All right then, acids and bases again. This is a good warm-up question. So 225 ml samples of unknown monoprotic weak acids, A and B, are titrated with 0.1 molar sodium hydroxide solution. So titrating, two different solutions. Titration curve for each acid is shown below. Which one's more concentrated? So what do the parts of the curve mean? More concentrated means more of what? More water, more acid, more base, more moles of acid. So more moles of acid. I'm adding the same sodium hydroxide to both of these. So if I add 10 mils, I've added the same number of moles of sodium hydroxide. Which part of the curve tells me how many moles of acid I had? Yeah, middle of the steep part, which is also called the equivalence point. So this part of the graph, at least to answer this first part, this part of the graph is what we're looking at. Because that's what tells me, like, that's the equivalence point. That's where my moles of base added equals the moles of acid that was present. So which one's more concentrated? Acid A. Because for every drop or milliliter, or however you want to think about it, I guess milliliters here, for every milliliter of sodium hydroxide added, I'm adding more moles of sodium hydroxide. As those moles of sodium hydroxide increases, when it gets to this point is where those are equal. And this one increases at like just under between 20 and 25, maybe 23, where the pH starts to spike. But acid A doesn't spike until almost 35 milliliters. So I had to add more of the same concentration, which means I had to add more of the base. Okay, so why is acid A more concentrated? How do I know acid A is more concentrated? Yeah, perfect. Okay, so that's the more concentrated one. Which of the two weak acids has a larger Ka? And now I got to think about, okay, which part of the curve tells me about Ka? This is more concentrated. How can you find Ka from the graph of a titration curve? Yeah, and for a monoprotic acid, middle of the buffer region. For a diprotic, then you'd have like two buffer regions. These at the top and bottom are at the buffer, or like this top one's not a buffer region because that's like where the whatever the strength of the base that you're using maxes out, essentially. Yeah, so and I think hypothetically this would max out at 13. But so middle of this, right, because this is the buffer region. The buffer is strongest in the middle. gets weaker as you go to either end, as you go use up more of the conjugate acid or more of the conjugate base. So middle of this is also the, so I don't know, I'm just going to eyeball it. There would be the, really it's the volume to reach, the vertical would be the volume to reach the half equivalence point. And then over here would be the pKa, whatever the pH is at that point. I drew that line really weird. Or it straightened out really weird. Should be like there. Why is that the half equivalence point? Exactly 1/2. We're thinking about like conjugate base, conjugate acid of my weak acid. So the thing that's making this curve. I'm adding more base. When I get to the equivalence point, do I have, I guess, what's the relationship between the amount of weak acid? How much weak acid, how much weak base do I have?
Isn't that the equivalent point the moles are equal for acid
and the strong base? Moles of acid and the strong base added, but the strong base that I'm adding is reacting with my weak base, with my weak acid. Let's see if I add my strong, this is not really an equilibrium, but so at the equivalence point, if I've added the same amount of base, strong base, as weak acid, how much weak acid do I have? Essentially, practically speaking. I had 1 mole of each. Those would react. How much weak acid would I have? If they react? After they react. Not the initial, but at the end. So initial, I've added in that same amount. How much of the weak acid gets turned into weak base? All of it. All of it. Right? Like these would react completely and I would have 0 moles. And then I would have 1 mole of A minus. So at the equivalence point, how much weak base do I have? Yeah, I was thinking weak acid, but I said weak base. You're right. Yeah. I have 1 mole of the weak acid. How much, sorry, 1 mole, wow. 1 mole of the weak base. How much weak acid do I have? None. What about at the half equivalence point? Half a mole of acid and base. So at the half equivalence point, I have the same amount of weak acid and weak base, regardless of how much you start with. So if this was, yeah, they're unknown. I mean, I guess we could have calculated it. I just made up numbers, right? So this is, at the equivalence point, this is all weak base. So at the half equivalence point, it's 50-50 acid, weak acid, weak base, which when we do the math in the Henderson-Hasselbalch equation, if base and acid are the same thing, the log of 1 is 0, so pKa is the pH. So which one has a larger Ka?
Acid is still right.
Still acid A. Larger Ka would be proportional to, at least, the larger pKa. So one of these is, this one A is like, I'll call it 5.8. This one is like 4.9. Seems a little bit closer. I don't know. So A is also the larger Ka. And you should be able to get, aside from the fact, like, I made up this number of moles, right, for the point, but from the graph, from the titration curve, graph of the titration curve, the half equivalence point tells you the pKa. The equivalence point tells you the moles. So we could have found exactly how many moles this is. And it's very similar for a weak base being titrated with a strong acid. Just the direction that it's going is reversed. So it'll start high and end low, but you will still have a half equivalence point that tells you what the pKa is because it's half acid, half base, weak acid, weak base. And the equivalence point will tell you the concentration of the, I guess, the total concentration of the initial weak base that you're titrating. Okay. Oh, well, I guess I knew this slide was next. Right, so if we're starting with a weak base, we start at a high pH. As it goes down, we'll get the half equivalence point, which tells me the pKa. And then, and this is actually, this will give me the pKa it's the H3O plus concentration, which we could at least use to find the pKa. Actually, I don't think it matters because the equations aren't reversed. You could still use Henderson-Hasselbalch equation, rearranges a little bit for pKb, but at the half equivalence point, it would be the same. Oh yeah, when calculating pH in the buffer region, use the pKa for the conjugate acid. So this would be the pKa of the conjugate acid. So that's the Ka, pKa of the NH4 plus. Because the whole graph is in pH. So what is the pH at the half equivalence point for the formation or for the titration of a weak base with a strong acid. pKb of the weak base is 8.75. So the first thing to dissect is, what is the pH at the half equivalence point? What does that mean?
That's pKa.
It's the pKa. Exactly. pH at the half equivalence point, weak acid or weak base, is the pKa, because the graph has units of pH as the y-axis. So pH at the half equivalence point, that means really we're trying to find what is the pKa. And how do we find pKa from pKb?
G minus pK.
Yep. Because 14 equals pKa plus pKb for the exact same reason that 14 equals pH plus pOH. So 14 minus pKb equals pKa. So 14 minus 8.75. So that's 5.25, which also equals the pH. Lots of little details. For polyprotic acid, which you guys saw in lab, if you titrate and the Ka1 and Ka2 are sufficiently different, which unfortunately the book doesn't like. I hate vague terms like that. It's like, well, what is sufficiently different? And it's kind of like when we can assume small x, so a magnitude difference of 10 to the 3. So if they're at least 10 to the 3 different, then you'll get two different curves, because essentially the deprotonation of the second proton is so small that we can ignore it. If the Ka1 and Ka2 are too close together, then we can never fully get this first equivalence point, because before we get there, we already start to lose some of the second proton. So these will just kind of like smear into one curve. Because after you lose the first one, it could lose the second one. If the essentially chances of it losing that second proton are really, really, really small, then it doesn't matter. But the closer that these points would get together, the closer the Kas get together. Actually, the closer these points get together, the less differentiation you have between the two. The other important thing to remember, which you guys did in lab, is that the first equivalence point and the second equivalence point takes the same volume to get to each, which is why you can use the second equivalence point to figure out what the concentration of your unknown acid was. Because it's the same moles, you just have to divide by 2. And that should make sense, because the amount of base, strong base, that it takes to remove one proton is going to be the same amount in moles to remove the second proton. You got to take away one proton and then come back around to take a second one. Some really good questions in here. So 3 different titrations. I think the best approach for something like this is find all the stuff that's the same, because then you don't really need to consider that across the 3. Just figure out how they're different. So these are all 25 mils. They're all 0.1 molar. And they're all being titrated with 0.1 molar sodium hydroxide. So what we need to pay attention to is the thing that's different, which is the type of acid that it is. Monoprotic weak acid, diprotic weak acid, and strong acid. So which of these is most likely to be true? Would it make sense that all three titrations have the same initial pH? Can kind of cross that one out immediately, especially considering that we have a strong acid in here. Like that's automatically going to be a much lower pH. So it can't be that they have the same initial pH. All three titrations have the same pH at their first equivalence points. Again, that's going to be dependent on what the Ka is, especially for the weak acids. I mean, maybe most especially for the diprotic weak acid, right? Because how do you calculate the pH at the first equivalence point for a weak acid? What's the only thing in solution at the first equivalence point? The only thing that matters, I should say. So if I started out with all weak acid, HA, at the first equivalence point, how much weak acid do I have? Hmm? Yeah, did I say weak acid or weak base? The point is, the weak acid, start out with weak acid. When you get to the first equivalence point, it's the first equivalence point because you added enough base to neutralize all the weak acid. So there's no weak acid left. So it's all weak base. So at the equivalence point, this will be 0. This will be, I don't know, a number. And so at the first equivalence point, you calculate the pH from the Kb. So you do A minus plus H2O. And actually, since we have this down here, because it's 0. Well, it wouldn't be molar. It's not even moles. They didn't give me moles. So you use the Kb equation, you plug in how much A minus you have, whatever the concentration is at that point, and then you calculate OH minus. So the titrations, to have the same pH at their first equivalence point, would all have to have the same Kb. Since they're different acids, not likely to be true, especially for the strong acid. Actually, for the strong acid, what's the pH at the equivalence point? 7. These will definitely be something other than 7. So it's not B, which leaves us with C. But does C make sense? Does. Why does it make sense? We have the same molarity, same initial volume, same molarity of NaOH even, and that first equivalence point, because I same volume, same molarity, have the same number of moles of each of these. The equivalence point, or I guess the amount of base needed to reach the first equivalence point, only depends on the number of moles of initial acid. The pHs can be different. They'll start at different pHs, but the volume of base that it takes to get there only depends on moles. Cool. Questions? So this might help with the lab this week, actually. Indicators. Indicators are usually weak acids or weak bases that just have a color depending on what the pH is. So like the phenolphthalein that you use for most strong acid, strong base titrations. And I think it's interesting to look at this. So we just said strong acid, strong base titration. The pH at the equivalence point is 7. But phenolphthalein starts changing color. It's like 8 point, call it 8.6. Or I guess it shouldn't change, not starts changing color, but starts to completely change color at 8.6. And this is why you want the faintest pink color, because it'll start to change down here around 7. You'll start to see the really, really faint pink. But then the more pink that it gets, the farther beyond pH 7 that you've gone. So that's why the best titrations are the super, super faint pink. And so phenolphthalein we use because it's sort of inflection point where it like really starts changing color. I think it's actually PK. Or it's equivalence point. The pH there ends up being, like I said, 8.6. But you can start to see that change before that, right around 7. But there are lots of different indicators. Phenolphthalein is just one of them. I actually used this in an organic chemistry class and had them draw out the mechanism for it because it's just a neat mechanism. So a lot of the times you get color in different molecules when you have conjugated double bonds. So right now I've got 3 different benzene rings, but this carbon in the middle can't have a double bond, otherwise it would have 5 bonds. So these are separate systems of electrons essentially. But when this pops off, when there's enough base, then I get this molecule, and now this carbon loses this bond with the oxygen. And now these double bonds can resonate through all 3 of these pi bonds, or all 3 of these benzene rings. And all of that resonance causes it to absorb light at frequencies in the visible range. So one little reversible bond causes this to change color. And we only use a tiny, tiny amount, so it doesn't affect the pH because this super tiny amount of acid that it would require to actually neutralize, or the amount of base that would require to reach the equivalence point for the phenolphthalein is insignificant. I mean, you're adding drops of a diluted solution to your solution. And I think because pKa is also above that, as you're adding base in, it's going to react with whatever your strong acid is first before it reacts with the weak base, which is the phenolphthalein. So it's only after you've completely used up your weak base, or it's only after you've used up your strong acid that there's any base available to react with the weak acid that is the indicator. Hmm. So another indicator here, methyl red changes from red to yellow, or yellow to red. Same sort of reason we're here with the Henderson-Hasselbalch equation, that you get a range of two pH values, or not a range of two different, like a range of two pH units. So one above and one below the pKa, just like a buffer, is only strong within that one plus or minus one pK or pH. And there's indicators all the way down the spectrum, and some of them even have double or two different regions. So thymol blue can go from red to yellow, and then from yellow to blue. Which one? I think my wife and I used thymol phthalate at our wedding. So, people do things where they like make the candle or whatever. We just poured two clear solutions together and it turned blue. Had safety glasses and everything. Yeah, so you use these at a range of, pick them for the pH that you're looking for. Oh, and actually, I think what I mentioned, thing that I wanted to mention with this as it's relevant to the lab. Actually, was that the part that we didn't do? Is that part 5 where you didn't do that? Or did we do this part? Where you have to determine you have to roughly determine the pH of one of the solutions based on the indicators that you add. So it changes over a range, is what I wanted to say. So you can't pinpoint a single, specific pH unit, but you can give a sort of approximate pH range, essentially 2 pH units, within which the Ka or the KEQ would exist for that complex ion. All right, and then I think this is the last solubility, or the last equilibrium topic for this chapter, is solubility equilibria, which I think are also some of the easiest because we're talking about things dissolving, which means that one of my things is always a solid. So like here I have calcium fluoride. You guys may or may not have memorized all of these different solubility rules, but depending on your definition of soluble, everything could be considered soluble, because everything dissolves a little bit in water. And KSP is the value that tells us how much that is. So for calcium fluoride, right, we can write out the dissolution equation, and the equilibrium for that, or the equilibrium constant for that, is still going to be products divided by reactants. But my reactant here is the solid. And because it's solid, we don't include it in the equilibrium. So KSP is just the products multiplied together, raised to their exponents. Don't forget that they're raised. Or raised to their coefficient, raised to the power of their coefficient. The other thing that makes solubility equilibria a little bit unique is that we talk about the solubility in terms of molar solubility. So how much of the ions is present, or how much of each ion is present in the solution. So we're going to use S instead of X whenever we're solving for these. You can calculate it from just straight from KSP. So if you added that solid to a solution or to water, the molar solubility would be how much of that actually dissolves, which is determined by KSP. But KSP is not the molar solubility. Like all of our equilibria, it depends on the temperature. And molar solubility can change depending on things like the common ion effect. So if you're adding just one thing to a solution of DI water, like what was this? Calcium fluoride. If you add calcium fluoride to DI water, you could use KSP to calculate whatever the molar solubility is. But if there's some other source of fluoride or calcium that's in the water, then that molar solubility will be different because it'll be suppressed by the other ions in the solution. So silver chloride, we think of as insoluble, and it does have a really small KSP. 1.77 times 10 to the negative 10 is practically insoluble, but it does mean that a tiny amount does dissolve. So if we're writing out an ice table for this, it looks very similar to our other ice tables, except that there's nothing in the reactants because my reactant is a solid. So just like water and all of the acid-base equilibria, we just leave it out. For good reason, we leave it out. So my KSP for this silver chloride will be S times S. S being the molar solubility. So my KSP is 1.77 times 10 to the negative 10 equals S squared. Square root of that. Raised to the 0.5. So 1.33 molar equals S equals molar solubility. It's not always, wait. We left off something super important. That's important. 1.33 molar would be ridiculously soluble. Impossibly soluble. So it's not always going to be quite that simple, but a lot of them are pretty simple when you're just trying to calculate molar solubility. So again, depending on your definition of what is soluble, which is why if you've played the solubility game that I made, there's some on there that are weird, like silver acetate and aluminum acetate. Wouldn't think of it as being insoluble, but they're insoluble on there. I'm working on updating that so it matches the textbook so that those things should always be soluble in this class. I just based it on another table. But if you look on here, like I think all of these we would think of as generally being insoluble. Some of them are really insoluble. Like the most insoluble on here is copper sulfide, which is times 10 to the negative 36, which is, I mean, 6.022 times 10 to the 23 is a mole. And this is quadrillion? Wait, 6 is million, 9 is billion, a trillion times. This is a trillion times smaller then a mole is large. So very, very, very insoluble, still technically not insoluble completely. But that's way, way out of the edge. So if you want to calculate the molar solubility for something like iron hydroxide, one of the most important things for doing these is actually writing out the equation. Unless you do so many of them that you can just see the equation in your head. So I want to know the molar solubility of iron hydroxide. So iron, which is my solid, it is in equilibrium with Fe2 plus 2 hydroxides. Super important. And since I'm starting out with 0 of each of these, some of this is going to dissolve a very, very tiny amount. Oh, sorry, not plus S, plus 2S. So now KSP is equal to, will be S times 2S squared. Just like with previous equations, don't forget that this 2, the square, applies to the 2 also. So this will be KSP is equal to 4S cubed. So 4.87 times 10 to the minus 17 equals 4S cubed. So take that, I divide it by 4, and then I'm going to raise that to the 1/3. So it's easier than trying to figure out if your calculator has, I don't know. I don't like the other than square root buttons and having to figure that out. It's easier to raise it to the fractional power. So this is going to be 2.30 times 10 to the minus 6 molar equals S. Meaning that if I add pretty much any amount of iron hydroxide, I'm going to get that concentration of iron 2 plus, 2.30 times 10 to the minus 6. What concentration of hydroxide will I have? 2 times that. Yeah. So 2 times 2.30 times 10 to the minus 6 will equal my OH minus concentration. So silver bromide in pure water, again, you want to have the equation just in case there's something you don't expect, but also because it makes it look like all of our previous problems that we've done with the ice tables. And if you can connect that to this, it'll be easier to remember. So 0, 0, plus S, plus S. So for this one, it'll be 7.3 times 10 to the minus 7 equals S squared. So, oh shoot, I did something wrong. Wait. Oh. Just rushing forward with reckless abandon. That's not my KSP. I'm supposed to find KSP. So the molar solubility then is what I was given. So 7.3 times 10 to the minus 7 times 7.3 times 10 to the minus 7, or yes, you could just square it. There we go. I'm pretty sure KSP is unitless, just like all of our other equilibrium constants, even though it says molar up there. Oh, right. Yeah. So even though like KSP is related to molar solubility, it depends on the stoichiometry. So you have to calculate the molar solubility. So like if we were comparing magnesium hydroxide and iron 2 carbonate, like which one's less soluble? Yeah, the magnesium hydroxide has a lower concentration, but it's going to produce more ions in solution, which is really what the molar solubility says. Like when I dissolve this, how many ions do I get per sort of thing in solution? And because of the hydroxide, you're going to get more, 3 ions, whereas you only get 2 for the carbonate. So you end up getting a higher concentration of dissolved stuff. And then they're just showing that that can be reversed here. So sometimes it will be that the KSP gives you the smaller concentration. Or actually, if they're related, like 3 ions, then the KSPs are comparable. So 3 ions, 2 ions for the magnesium hydroxide and carbonate ends up flipping those. If they're far enough apart though, it won't flip. So if that makes sense, then you can know when you can just compare them directly and when you don't have to actually do the math to calculate molar solubility. All right, cool. Friday, we'll talk about the common ion effect.